message is already dropped on the WhatsApp group. And today's lecture is the last lecture on first unit of artificial intelligence, knowledge representation and reasoning, date 20 September 2021. Okay. So what first I'm going to take a simple overview of the syllabus of AIKRR first unit. Just an overview means what points were there, what we actually discuss, and what is remaining. Okay, so in AIKRR first we discuss about the history of, obviously I have not gone into the detailed history date wise. Instead we have simply seen what this history is. So this is our unit number 1 for AI, where we are an overview and historical perspective, Turing test. Then we go with the physical symbol system and scope of symbolic AI. Then we also define what is agent in AI, and then we start with the search algorithm, that is depth first search, breadth first search, and today we are going to see DFID, or what is called as IDDF also. So likewise, so we are going to see this. So let's see what is the state space search. Okay. So let's check with the thing. So I'm just going to what we say, that whenever we say artificial intelligence, what is defined by definition. Whenever we say artificial intelligence, by definition we are saying that we are making machines, okay, which are capable just like human being, right? Or we are trying to make machines which are capable just like human being. It happens now and then. We'll start this. So when we say this so here we are saying what is this artificial intelligence. Okay. So artificial intelligence, AI, is the branch of technology, branch of tech, actually computing technology, just not simple, you can say computing technology, which enables machines, I am using short form, okay, to mimic the human behavior, okay, human behavior, or you can say it can mimic the human, or you can make machine think, and likewise. So AI is specially for problem solving. लेक्चर चल रहा है फोटो त्याच्यातच करायचं ते पूर्ण टेक्निकल इव्हेंट आणि विजनरी द्यायचा पार्टिसिपेट करायचं ते सांगतो so what this AI is for, so AI is basically goal oriented. So there are certain tasks that human being can carry out, and those tasks can be considered as a goal oriented, or problem solving. So whenever we say AI is basically goal oriented or problem solving, what you can say approach. So you take a particular problem which is not computable or not solvable using a traditional computing or what we call as a computer engineering, and there we use the AI fundamentals. So for problem solving, this AI to create the knowledge base, to acquire the knowledge, I generally go with the state space search. So let's try to understand this state space search. What can say philosophy. So let's consider that this is the space that you are having. Okay, and in this space you are having what you can say different nodes. This is node 1, node 2, okay, so node 3 likewise, and you are having here say node this, you may have some node here. Okay, intermediately we are seeing that in this space we are having actually infinite number of nodes. So this is, say suppose this node is your starting state, this node is your starting state, and from this node onwards, and say suppose this is your goal state, or this is what you want to achieve, and this is what is your current position. So the approach of state space search, okay, let me type this state state space search is such that it can try to accumulate all the knowledge in a given space. So when it accumulate all the knowledge in a given space, from this what it chooses the expansion. So it chooses the complete breadth, and it explores all the nodes. It explores all the nodes in this breadth. Okay, so it goes on creating for the thing. So it go on and it acquires. So suppose you are having say infinite number of nodes here. Okay, so obviously your depth will be infinite, means you don't know how much how many nodes are there. So what is the time complexity for this? If you go with the time complexity, which is generally gives by big O, of you are having this b, and we can say 2 power. So I'm using this power sign, raised to power d. So this is the thing, b is the breadth and d is the depth. Okay, so number of nodes and the depth of that particular graph or particular tree is considered as a times complexity. Now let's say suppose here you are having only one element. Okay, this is your start element, this is your end element, and this is your what you can say goal element. Okay, let's call this as a S, this as a G. Okay, and this is the intermediate element or not goal element, so we call this as a I. And this is a simple graph, which is the special graph which we call as a binary tree. In this case, what happens if you go with the breadth first search? I'm just changing the color. Now, when we use the BFS, breadth first search, what happens? From the start node, it chooses the entire breadth and it goes to this, and also at the same time it explores the G. And because it reaches to this G, the search stops here. So the time complexity for this searching is a lesser. But if you go with using the depth first search, what happens? It goes first, say suppose to this. Okay, it found no what you can say node here to travel, so it will backtrack on this track and then it will go here, then it will go here. So if you see in DFS you are having 1, 2 and 3 operations. Okay, in DFS you are having 1, 2 and 3 operations, but in BFS you are having only 1 and 2 operations. So BFS is a little bit faster than depth first search, but the BFS is actually starts unless and until all the nodes not get visited. So if say suppose in this space you are having around, say this is say if you go with like this, you will have almost few factorial things. So if you are having say 100 nodes, you actually have to go for 19 factorial time combination. Okay, just consider this. I'm just making this disappear so that we can try to see how this depth how this state space search actually work. Okay, just consider the 8 puzzle problem. Just consider a simple 8 puzzle problem where you are having this what you can say 3 by 3 mm, square. Okay, and in this 3 by 3 square what you are having, one, this is empty space, so you are having this 1 2 3 4 6 5 8 and 7. So you got this. Now your final stage that you want is like this. Okay, we are considering this is some random start state, and this is what your final state is should have to be there, and that final state is what you are having this empty space here. Okay, empty space here, and here you are having 1. Okay, here you are required 2. Just consider that you require 3 here, then you want 4 here. Okay, then you want 5 here, then you want 6 here, and you are having 7 here, then you are having 8 here. So what artificial intelligence do in algorithmic way in using Bfs and Dfs is try to find out the space here. So if you see the rules for this, you can move this hollow space, empty space, either in upward direction, yeah, or towards your left, or towards your right, or you can have this in a downward direction. So this empty space can move in this 4 direction if it is at a center. Empty space can move in 4 direction if it is at the center. When it is at a corner, it can move only in 2 direction based on the corner. Okay, if you are in the upper so what you can say left corner, it can move downward and rightward. If it is a upper right corner, you can move leftward and downward. If it is a like this, so you can move that particularly. If it is in mid way, that is if you are in the position 2, 6, 8 and 4, you can move in leftward, rightward and downward, or you can move leftward, rightward, upward, or you can move leftward, rightward and say downward, just way. So when we see this, for this, if you consider these 3 element, it's actually take almost 3 raised to power 20, almost 3 raised to power 20 combinations to reach from source to destination possibility. So for example, now if you go with this thing, so here we are having what one this empty space can move in a leftward direction or can move in a what you can say outward direction, upward direction. So we are having 2 possibilities here. So let's draw these 2 possibilities. Okay, so here you are having these 2 possibilities. Okay, here what we will have state space searches, that is what we will have here. These are the field 1. Okay, this say suppose these are the field 1, and you move this space in upward direction, and here you are having the another space diagram. Now this diagram, here you are having what you can see your space is moved in leftward direction. So now the space occupies the leftward direction. So space occupied the leftward direction. So this space moved from corner towards center. Yeah, here to upward. And so if you see here, you will get once again 2 possibilities, because this is already moved, you are not going to move back. But if you go on move back and something, then this can be called as a loop, and it can go into what you can say infinite loop. So this is what we call as a state space tree. BFS and DFS are used in this state-based tree. For example, if when you go with the BFS consider these two branches at the same time. Breadth search considers these two branches at the same time. But if you go with a DFS, what DFS will do? DFS will keep expanding only one branch. So it expanded this branch, it will not consider this move. In depth first search, this is not considered. Then it will go on expanding only in singular direction. So what you can say, you first move this, suppose say space from corner to right, then you will move this space at this position from this position to we can say right, then you will move this space in upward direction, then you move this space once again in upward direction, and this goes on. So in depth first, what happened, the uh, puzzle may not get solved completely, and that's why it's called as also incomplete search. You got this? Hello? Am I audible to you?
Yes, sir.
Yeah. So you got this state-based search, 8 puzzle problem.
Yes, sir.
Okay. So what these AI people do, for example, let's say suppose you start from Delhi, hmm, and you want to go to Chennai. You want to go to the Chennai. So we are having here in our complete India. Here we are having what? Our India. I'm just trying to draw the map, which may not look exactly because like of Indian map, but just consider that this is India. You are here in Delhi and you want to go to Chennai. Okay, so this is your what you can say space. This is your space. Now, what if you go with the entire space? What will happen? If you go with the entire space, what will happen? You need to your time complexity will be exponential. It will be very hard to process. So instead, what we do, we know that is this is Delhi and this is Chennai. So we try to cover a space which actually includes Delhi and Chennai only. So what this is called as a bounding. So what happened when this bounding is done? We actually what you can say deleted this portion from the what you can say available state space, because we know that there is no what you can say huge traveling in this portion. Okay, you will never reach to the Chennai. So you know now this is the only thing. So what we have, bounded breadth first search. What we call this as a in AI as a bounded breadth first SAR search. This simply means that the bounded breadth first search means that, say suppose you are at Delhi, okay, and here you are having say Jaipur, here you are having Agra, here you are having Bhubaneswar, okay, here you are having say some random city, okay. So random city which is not, now you got all these cities connected to Delhi, all these cities connected to Delhi, and your goal state is in a Chennai. Goal state is in a Chennai. So you want go from you can say your Delhi to Chennai. Now, as per this bounded, what we'll do, we will go, instead of going through all the bread because it will do require more operations, this algorithm, this approach of bounded breadth first, try to divide these into two parts. Consider that is, let's say suppose these are divided into two parts. So instead of going through all these four in a one bread, it will only check for this. It will only check for this. Okay, and then it will check two on the element. So if lucky, it may be once I reach to Delhi, or sorry, Chennai, or it may go on, let's say suppose if we consider this as this state space which was we can say decided. Okay, so you are actually you are trying to exclude this from this breadth. So if you are having say n element, saying is that n element मतलब आपके पास अगर 100 cities है, so instead of going through all 100 cities, you will select only first 50 cities to check whether the things exist or not. If things won't exist in this first 50 cities, then you go on expanding your space for a search. For example, if Chennai not fall into this space, then we go on expanding and we will expand it to like this. Okay, we'll go on expanding if not found like this. Let's say suppose this is here Chennai is there. So what happened in first try, in second try, and in third try we got the solution to our problem. This is bounded breadth. मतलब instead in a graph you are having, if you draw a simple graph like structure here, that is in a graph you are having say these 4 or 5 nodes. Consider these are the nodes in a graph. These are the nodes in a graph, and they are connected. Okay, they are connected with each other. We are considering this connection like this. It's not always necessary to have the same graph in every example, so I have drawn graph in a different way. Now you connected, but now you want to go from this source, that is what you can see your current position, to the destination. So let's say this is your destination, to the destination. So what this bounded will do, this bounded bed first search will do, it will say no, it's not necessary to go through all the and what you can say k elements. So it will only search in this space. If the solution is not available, obviously it is outside this selected space, then only it expand itself to the next what you can say possibility of the space. So instead of searching for all nodes, the this bounded breadth first search go by piece. मतलब हमारे खाने के थाली में बहुत सारा खाना होता है, हम एकदम से नहीं खा सकते, तो व्हाट वी डू, वी गो पीस बाय पीस. यस, या टू फिनिश इट, हम वैसे ही करते हैं ना.
Yes, sir.
Yeah, so this is a simple way of this. Now in the same way you are having the bounded depth first search. Means let's say suppose here you are having these nodes, first node, the second node, let's consider this is third node. There are other nodes also, then you are having the fourth node, and let's say suppose in this you are having this as a kth node. Let's k be sufficiently large number. ऐसा समझो कि k का नंबर 1000 से ऊपर है, and if you go with a DFS you will go from source to intermediate, intermediate to intermediate, intermediate to intermediate, intermediate to intermediate, and you go on from this intermediate to this 1000th node. Now say suppose your goal node is here, goal node is here just next to this node. So actually you are spending your time in a wrong direction. You are spending your time in a wrong direction. You will never reach to the goal. So what happens in bounded depth first search? Okay, what happens in this bounded depth first search? Okay, in bounded depth first search, what happens? The instead of going through these all these, it says that the depth first search will continue only for some, let's say if there are n element, then some n minus k elements only, or n minus k level only. Okay, means this is called as in a tree, root level is called as 0th level, this is level 1, this is level 2, and as we say that this is level 1000. Okay, now if 1000 is the n, capital N there, then this k may be something sufficiently large which can reduce this 1000 to below 100. So let's say this k is equal to 901. Okay, so this depth first search will only continue till the maximum 99 what you can say elements, and afterwards it backtrack and it will go come here to the result node. So this bounded depth first search and bounded breadth first search, this actually help in reducing the time. आपको समझ में आ रहा है?
Yes, sir.
Yeah, आपको समझो from from Pune you want to go to say Mumbai, okay, and you go with a depth first search. तो आपने गाड़ी शुरू कर दी, आपके पास कोई जीपीएस वगैरह का कुछ नहीं है, बिकॉज दिस इज अनइनफॉर्म्ड सर्च, सो यू आर नॉट हैविंग एनी प्रायर नॉलेज. So you started your bike and you go on, you started towards नगर. तो आप पुणे कभी पहुंचोगे ही नहीं, क्योंकि आप मतलब मुंबई कभी पहुंचोगे नहीं, क्योंकि आप पुणे से नगर जाओगे, नगर से औरंगाबाद जाओगे, औरंगाबाद से okay, well, earth is round, but yes, the round earth also has the sea and oceans. So if you are on bike, it's quite impossible to reach Mumbai if you take the route to towards Nagpur. Okay, अब आप अगर 100 200 500 600 किलोमीटर आगे चले गए तो चलेगा क्या? So simple thing, that is once you started to get intuition that you are on the wrong way, we generally takes what the U-turn. Depth first search is the U-turn. Okay, so आप पुणे से स्टार्ट किया, आपको मुंबई जाना है, but you found that nothing is appearing or giving you the idea of Mumbai. So what will happen? You may either U-turn from the Nagar or from Aurangabad, and so you once again come back to Pune, and then you will get the other way, which will direct you to the Mumbai. So this is bounded depth first search, which actually try to minimize the time complexity of the depth first search. In the same way, in a bounded breadth first search, आपके पास समझो n नोड्स है यहाँ पर. It's quite cumbersome to visit all the nodes. समझो this element is your source, and this element is your destination. Now in first thing, it will go on all the beds, so it will be explore this and this. After that it will go on exploring, even it get the goal state, then it will go on exploring this. So instead of exploring all in bounded, what happens, it can make two sets of these elements. So it said, okay, first explore only for this part. If the solution won't have available here, then go in the next part, what we call as a binary type function. आपको बाइनरी सर्च पता होता है ना, वो एलिमेंट कहाँ होगा इसका एक अंदाजा लगा के ये करता है. So it's try to define the breadth and it's try to limit the depth. This is the difference. In bounded breadth first, it try to define the breadth of the you can say search, and in a bounded depth first, it try to limit this you can say this search. Now there is the combination of these two, Bfs and Dfs, okay, again with the added advantage of bounding or bounded search, and that is called as iterative depth first search. Sometimes it's called as depth first search iterative, okay, or this called as DFID or IDDF. Okay, so this what in your syllabus is called as, let me see, because the same algorithm is known by different name by different scientists, so we should have to respect that also. The same algorithm is, so some call it as iterative deepen depth first search, IDDF, okay, or some call this as a depth first iterative deepen search, okay, this DFID, depth first iterative deep search or deepen search. So these are some called these are the iterative difference. So the name is DFID or IDDF. Okay, so we are going to see what exactly that is. So I'm just drawing here the graph or a tree. Tree is a special graph. We are having some nodes here. We are having some node. This take the combination. We are having certain nodes. Let's consider these are connected. Let's consider these are connected nodes. So this is our graph where we are having this node connected. So how this actually work? This is a combination. This search is actually combination. I'm just changing color so that you can get the thing. Now consider this as your goal state. This as your goal state and this as your start state. This as your start state. Now we will go with the traditional depth first search. How traditional depth first search will do? Traditional depth first search will go from start to this node. Okay, and there is a child node available here, so it will go from this to this. Then there is a child node available for explorer, so then it will go from this to this. Yeah, afterward it have no nodes here, so it will return back here, then it will return back here, and you know the stack is every this red arrow means one operation, so it's returned back to so you are having 3 edges, 6 operations. Okay, first forward traversal, then reverse traversal. Okay, so if one traversal require 1 minute, you actually spend 6 minutes here unnecessarily, and then you will go to this 7, and after this 7th you will go to the goal state. Okay, because you reach at the goal state and it is reached, there is no necessity to go afterwards. Okay, but if you are using the traditional, if you are using the traditional DFS, it will explore this also and then this also. Okay, so it will go there and then come here and then go here likewise. So this is what I can think. So here at goal state you stop. This is in your traditional approach. Now when you are using DFID or what we call as a IDDF or this depth first iterative deep search, we consider in terms of what you can say combination of breadth first plus combination of depth first. So for traditional we reach to the goal state using 1, 2, 3, 4, 5, 6, 7 and 8 operation. Means consider for traditional we require 8 operation. If you consider one operation equal to 1 minute, the time required to reach to the goal state using this simple depth first search, okay, is 8 minutes. Now just consider the breadth first search. Okay, traditional breadth first search. Here you are having this, I'm using the different color for breadth first search. You are having this start node, so it creates the complete breadth. Now it goes visit this and visit this. So you have done 2 operation. Yeah. After this, it will go on selecting the breadth of this. Go on selecting the breadth of this node. So for this node, this connectivity is there. This connectivity is there. So it will go on selecting this node. Okay, here you are having this connectivity. Sorry, then it will select this node. So you are having this connectivity and it will reach to the goal node. So the operations required are 1 and 2. Okay, 1, 2. Then you are having 3 and 4 operation. So you got 4 operations for breadth first search. Okay, we are not considering that it will go to the to reach the goal state. 4 operations are required by traditional way to reach here to the goal state. Okay, now we are going to see the IDDF, or what we can say is called as iterative deep, some called deepen. Okay, uh, depth first search, it, or it also called as depth first iterative deep or deepen search. Okay. It's also called as, this is the third approach of doing the things. Now I'm just choosing the different color for this third approach. How this third approach works? Third approach, I'm using the green color here. What this third approach is doing, it chooses the combination of Bfs and Dfs. So it chooses for this first, it chooses only the breadth. It chooses only the breadth. Okay, when it chooses the breadth, it says that okay, for this breadth we are having this 1 and 2 element only, 1 and 2 element. So it will traverse to this element, it will traverse to this element only, and then it will take, it finds there is no goal state available, it finds that there is no goal state available, so it will what you can say, travel to this without taking U-turn, because here you won't require to take any U-turn. Without taking the U-turn, it goes to this, but it uses the depth first iterative deep search. So instead of considering all the breadth at the same time, it now consider only the breadth of this. Okay, and it will reach to the goal state, it will reach to the goal state in only 3 operations, in only 3 operations. It stops actually here. Okay, these two not stop actually at these times, it actually go on exploring all the nodes. So whatever the time given here is lesser than the actual time taken by the DFS and BFS. Okay, so for BFS, if you go with this 1 2 3 4 5 6 7 operations are required, and for depth first search, if you go with this is 8 9 and 10 operations are required. So instead of 10 and 7 operation, this actually get completed within 3 to 4 operation when you are using the iterative depth first search. So what iterative depth first search is, the combination of BFS and DFS. You got this? If you not,
हेलो सर,
yes sir.
पता कैसे चला कि आगे गोल नहीं है ऐसा?
हाँ
मतलब ये देखो अभी हमारी गोल स्टेट है ना, मतलब गोल नहीं,
एक
इनिशियल
मिनट,
स्टेट।
हाँ इनिशियल स्टेट उसका क्या?
उसके बाद उसने दो पाथ लिए ना, 2 नोड्स पे गया वो।
हाँ तो वही तो मैं बता रहा हूँ ना, देखो अभी ये इनिशियल स्टेट है, ठीक है, हम यूज क्या कर रहे हैं, DFID कर रहे हैं, यूज इटरेटिव डीप फर्स्ट सर्च. सो फ्रॉम स्टार्ट इट विल गो फॉर दिस टू स्कोप, इट विल कंसिडर ओनली फॉर दिस ब्रांच. ओके, सो ये क्या करेगा, यहां से एक्सप्लोर करेगा इसको, यहां कुछ भी नहीं है तो ये यहां आ जाएगा सेकंड ऑपरेशन, एंड देन इट विल गो टू दिस नोड ओनली. तो जब ये
आगे
हाँ
मतलब आगे नोड है ना एक,
कहाँ नोड है,
उसके आगे एक नोड
ये
है।
ये जो नोड है, ये नोड बोल रहे हैं ना आप, then what happens in this iterative consider only this portion at first, of the graph. ओके, ये इससे आगे नहीं जाएगा, ये इससे आगे नहीं जाएगा. It will reach here and then it will reach here. Afterwards, it will consider this portion. It will consider this portion level wise. अभी यहां पर कौन सा है, ये लेवल 0 है, ठीक है. दिस इज लेवल 1 एंड हियर यू आर हैविंग लेवल 2. तो ये क्या करेगा, ये लेवल 2 में ये भी अपना गोल स्टेट भी लेवल 2 में है. ओके, सो इट विल गो ऑन दिस लेवल 2. तो ये क्या करेगा, राइट नाउ पॉइंटर इज वेयर एट दिस स्टेज, so it will directly reach here. So once this goal state is reached, it will stop all the operation. हम जब IDDF और दिस IDDF और DFID यूज करते हैं, तो what happens, once we reach the goal state we stop the operation. In traditional we won't do that, we actually explore all the nodes in a given graph. मतलब आपके पास अगर 100 नोड्स है इस ग्राफ में, लेट मी एक्सप्लेन यू दिस थिंग. ट्रेडिशनल में क्या होगा, आप इधर जाओगे, इधर जाओगे, ठीक है, इधर जाओगे, यहाँ कुछ नहीं है, फिर वापस आओगे, फिर इधर जाओगे, फिर इधर जाओगे, फिर यहाँ आओगे, इसके बाद नीचे आओगे, गोल स्टेट इज रीच, you registered a goal state because, but this is traditional, so you will go here and then you will go here and then you will say okay, goal state is here, but you actually explore all the nodes in a given graph. Now आपका अगर ये है ब्रेड फर्स्ट है, तो फर्स्ट you will try to explore all the adjacent node, then you will go on exploring all the adjacent node, then you are go exploring all the adjacent node. So whatever, even if you reach the goal state, you will try to register all the routes, cross links and everything in the breadth first. But when you are using iterative, what happens, here you will consider the first breadth. ओके, फर्स्ट ब्रेड कंसीडर करोगे ब्रेड फर्स्ट सर्च के लिए, आप एक्सप्लोर करोगे इन दोनों को. बट हाउ, यू विल एक्सप्लोर ओनली दिस एंड देन यू विल कम डायरेक्टली टू दिस. यू टर्न लेके आप यहाँ आओगे, तो आपने ऑपरेशंस कितने किया, दिस इज 1 2 एंड 3 ऑपरेशंस हुए आपके से. आप स्टार्ट से यहाँ आए, यहाँ से स्टार्ट को गए, स्टार्ट से इधर आ गए. ओके, सो नाउ योर करंट पोजिशन इज दिस, your current position is at this node. So you will consider now expand, because goal is not reached, you will expand the breadth. Okay, तो आप लेवल 2 के लोगों को इसमें इंक्लूड करोगे, दिस एंड दिस 2 nodes are included, but because your current position is here, you will not go back because these are already visited, you will go forward, and because you already reached here, which is the goal state, you will not go back and do all the operations. You will not go back and do all the operations. So this iterative will actually reduce the time. It's actually reduce the time and the memory requirement to store the path and other details. This is like ये knowledge gaining के लिए होता है. You got this?
और हाँ सर, अगर वो जो गोल है वो दूसरी साइड में होता तो,
हाँ, गोल
गोल
हाँ,
दूसरी साइड में,
तो दूसरी साइड में होता तो उसको वक्त लगेगा. बट इन दैट केस यू हैव द ऑल कॉम्बिनेशन, बिकॉज व्हेन वी से स्टेट स्पेस ट्री, व्हाट वी आर हैविंग, सेट ऑफ ऑल नोड्स. ओके, सेट ऑफ ऑल नोड्स व्हिच आर गिवन बाय दिस, यस, देन वी हैव सेट ऑफ ऑल एक्शंस. ओके, मतलब हम S1 से S2 की तरफ जा रहे हैं या आ रहे हैं, वो जो ऑप्शन है, दैट इज यू आर हैविंग द लिंक S1 to S2, or you are having link S2 to S1. So all set of options रहेंगे, so you will get the things, but no matter how, मतलब आप जितनी भी बार सॉल्व करोगे, because here we are having only few elements, here you are having only few elements. If you go on using n elements, let me n elements मतलब आप बहुत सारी, एक काम करता मैं, आप जो बुक है उसको ओपन करता, सो यू विल गेट द थिंग्स करेक्टली, कि उतना कॉम्प्लेक्स डायग्राम ड्रॉ करने के लिए वक्त नहीं है अपने पास. So what this state PDF, sorry, this state space search will do combination DFID. Yeah, hang over. It's not responding. PDF reader is not responding. It will take a little time because the file is big file. Course this first course in this first course in artificial intelligence. This is what we are talking about. So the time complexity. This is the what we call as a DFID or iterative depth first search. Okay. So हम जब ये करते हैं, just have to show you the diagram. Here I have shown this time complexity for this. So when it goes to branching with factor of 5 at depth 5, there are 5 into 5 minus 1, 21 nodes are there. So the exponential things happen. It is not only that you will have the 2 or 3. Here you go with the breadth first search. हम जब breadth first search से जाते हैं, this is your start node and this is your goal node here. Okay, but क्या होता है हम जब इसे यूज करते हैं तो we start here and we actually got what is the 3 adjacent node. So we visited all the 3 adjacent node. Okay, then these 3 adjacent node have all these dotted lines are for cross links. So you are having all these nodes visited, and then again you go on visiting all these nodes, even your destination node is here. But now if you are using here the combination of depth first and breadth first, what happened? I'm just changing the color. Okay, it will select this. Okay, once this is selected, it not go breadth first, instead it go with the depth first something. So it will go first to this, then it will go to this. Okay, U-turn, then it will go to this. Okay, if they not found the goal node here, iterative depth first is there. So whatever your current position, you only go to that. So it will go onwards and you can reach to the destination sooner than comparative to the other things. And if you see this here, if you go through the book, this is how this can be considered. Let's say I'm just showing you the state space first. Change screen. Here you are having the complete so here you are having the state space tree. Okay, so right, up and left, that is what you can say. Then here you are having this, so you get this complete state space tree, and this is your goal state. Now to reach this goal state, if you start from here, okay, combination are too many. So if you go with this what do you say, DFID, iterative depth first search, you will go on doing the iteration, and because you are bounded also, you will take the U-turn very early, and so the time complexity is lesser. Here you are having this graph. Okay, so if you see, this is as a start node, and if you are in the depth first search that you want to reach to this goal, and first say luckily you choose C, and from this C you directly choose G. Okay, path registered is SCG. Okay, you have not visited any of these things. Now you choose A, you choose B, you choose D, you choose E, and then you go to the G. So this path is possible, or you can go from SBDG, or you can go from SAEG. So it's totally depend upon how your depth first search actually go. So when you said here when I say that is there is possibility that you can go through this. Yes, there is always the possibility that which path you choose based on that. But comparatively, when you are having a very complex and what you can say very high number of nodes, okay. For example, if you are having number of nodes shown like this, a very dense number of nodes, very dense number of nodes, like this. So this is your goal. This is your goal. And say suppose this is your start node. So for this start node, let's say suppose you try to find out all the adjacent node. Okay, all the adjacent nodes. So all adjacent nodes are found 1 and 2. Let's say these are the two adjacent nodes. For these two adjacent nodes, you go on finding the other adjacent nodes and likewise. And so what happens? You are actually visiting these nodes unnecessarily. You are actually visiting these nodes unnecessarily. Yeah. So what if you choose the combination of both? Means you choose this and you go with a depth wise, then you will reach here earlier. So it shows here the difference that breadth first search will find this quickly while depth first search will take long time as it sweeps from left to right. So depth first search will find this one path while breadth first search will need to wade through exponentially growing layers. So DFS is on a finite tree. So if the tree is finite, मतलब जो tree होता है, if it is having a few number of elements, ग्राफ में अगर 4 या 5 cities है, then DFS is what you can say efficient. But if in a graph you are having larger number of cities, let's say 1000 or 10,000 something, then BFS is fast. In that case, BFS is fast. तो नंबर ऑफ एलिमेंट जब छोटे होते हैं एग्जांपल्स क्लियर करते वक्त so what it seems that DFS is more efficient than BFS, but the case is completely reverse. Okay, so what we are trying to get that we are actually using the combination of DFS and BFS, combination of DFS and BFS, and we try to reach something which is more superior to both, मतलब superior than DFS and superior than BFS. So we get the peak performance. If we combine these two, we get the peak performance. So we can say that DFID is more what you can say uh, I think this is the time complexity. This called as a number of branches. This is the depth of the tree. So if you see here and if you draw this in terms of tree in the connectivity, whatever is shown, then you can say that it is something which is having the more connectivity. We are not always working in a binary format. Okay. So if you have unimaginably large numbers, okay, can pose a number of choice that we find difficult to comprehend. So if you go with the search problem where, so to find a solution, this algorithm may have to examine 10 raised to power 20 nodes. So how long this will take? Just consider that 10 raised to power 20 means how long. Okay, so that much of times is actually 10 raised to power 6 years or a million years. मतलब हम अगर हमारे पास एलिमेंट्स ज़्यादा है when we have these many elements, so here you are having 1 2 3 4 5 6 7 and 8 elements. So we are actually using around 7 factorial is the possibilities of the weight. Okay, 8 minus 1 factorial. We are on the total 7 factorial elements are ways to do this search. So if you as this number of elements grows, the number of operation grows. For example, here you are having only 3 elements. For this 3 element, for 4 element here are 3 paths. So from start node to this to this to this, then you are getting U-turn, say 4, 5th and 6th. You are doing 6 operation for 3 paths. So if there exists n minus 1 path, you at least have to do twice operation. At least have to do twice operation for the single path selection. Now if you go with the n path, n minus 1 path, we are actually doing twice n minus 1 into n minus 1, so it goes into factorial. So the total operations required will be very high. Up, so getting this total operation required will be very high. For example, if you go with a very large number, okay, that is that you have the fast machine on which you can check a million nodes a second, okay, as for this 10 raised to power 20. So you got this. The complexity of problem is very high, and so this DFS and BFS are combined together. So what happens here? It first opens the BFS, okay, but then it goes by DFS like this. So it is a combination, okay, it is combination, and this combination actually gives thing. Then we have this depth bound DFS and depth bound, what you can say, bound DFS and bound BFS, which can be used. So depth first iterative deepening or search, what it does is that combines the best features of all the algorithms, and it does a series of depth first search with increasing depth bounds. Okay, so what exactly happens is goes on increasing the bound of depth, binding of the depth. So what happened exactly here, if you go with this state, I'm just making this, it uses the BFS here. So first bound is I'm just showing the bound now. So first bound is this two element, so it goes here, first operation, nothing is there, so it come back here and it goes here. So now the next bound is this, are these two elements, next bound are these two elements, but your final search was here, so you first go to this, and because this is bound element, you already got the goal state. So how many operations you have done? 1, 2, 3 and 4 operations. Now as you said, okay, that is, what if it select the other thing? Now just consider that it goes with the reverse thing. Instead of selecting this, here I have here 1, 2, 3 and 4 operations. Now first bound is here, so it goes to this first, goes to this first, yeah, then from this it will go once again to the start and here. Okay, now you are having the second bound for this, second bound for this, it will come here, but because this is the only element that available in this bound, it will go this way, 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 and it will reach the particular operation. So if you consider these operations, if it goes here 1, 2, 3, 4, 5 and 6 operations. So within 6 operations, within 4 to 6 operations, within 4 to 6 operation, it reach to the goal state. Now if you go with the simple what you can say, this depth first search, you will go from this, say suppose you choose first this path 1, okay, then you go 2, 3, then 4, 5, 6, 7 and 8. Minimum operations required if you choose this left is the 8, and if you luckily choose this 1 and 2, 2 operations, so it, if you get, what is your range is here 2 to 8 operations, 2 to 8 operations. But then if we consider that in this bound also, if you go with this state, you are, instead of having this 4, you get the 2 to 6 operations. So if you consider, you are the maximum number of operations required in iterative depth first is lesser than depth first search. You are getting this?
Yes, sir.
Okay. So that's why this DFID or iterative search is considered as more efficient. It is the and it combines the what you can say thing. So this is just the pseudo code that is you can write to explain the this algorithm, or you can simply write text by something. And when we are having this quite what you can say gray, these things can be used to solve the problems. For example, here you are having this queen problem. Okay, so you know that is queen, you have to place 1 2 3 4 5 queen problem is here. Okay, you have to place these queens in such a way that they should not have to cross the path. मतलब ये क्वीन का पाथ ये है, these queens path, these are the queens path. Okay, the path hai and this path is here. So this queen is not killing anybody. This is a goal state actually. Okay, क्योंकि क्वीन कैसे जा सकती है, in this direction, 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 in this direction. Okay, so we can say upward, downward, corner side. So these are the way a queen can go. So you have to place this 5 queen. So if you are given with a random state, means if you are simply given with a simple 5 by 5 matrix and you have to place the queen 1. So if this is your first state, that is your queen occupied this position. This queen occupied this position. To place the second queen, you may require to go through different decision making, what you can say, strokes, and out of these only one is correct. Out of these only one is correct. Okay, this is the only correct positioning. This is the only correct positioning, because this positioning only can allow you to have this positioning and likewise. So if you go with this, you will get the different goal steps. Okay, knight's tour, or what you can say, think queen problem is the n king's problem to place n queen. So this is what about thing. Now here you are in this board checkerboard problem is there, that is 25 pin solution is there. Okay, you have to it's a rabbit leap problem. They have to leap in such a way that you have to have these 3 rabbits here and these 3 rabbits here. Okay, they are crossing stream, stones placed in the east direction in a line. Only one empty stone between them, and it's required to be there. So there's what conditions are given. The rabbits can only move forward 1 step or 2 steps. They can jump over one rabbit if the need arises, but not more than that. So this rabbit can jump at this place. Okay, and this rabbit can jump on this place. Only one rabbit this can jump over. Yeah, so in this way you have to migrate all these rabbits, means all these 3 at this place and these 3 at this place, then game is over. So in such type of simple games which require thinking and likewise, you can use this state space tree and uh, DFS and Bfs. In decision making also this can be used in this can also be used in grabbing what you can say the thing, let's say designing the things. It can be used to collect knowledge base, create the knowledge base in a robots, so that a robot will come to know that how to move, where to move and likewise. And this is what the entire we can say intention behind learning these things. So we will start the heuristic search and randomized search in from the next lecture, because our first unit is over. Okay, we will have the immediate test on the first unit in the next lecture. Okay, so I will so give you the some questions, and within 1 hour you have to solve those questions. Okay, I will put that not in actually lecture on classroom. Okay, so we continue the lecture with heuristic search, but in classroom you will get the test 1 for these things. This test is something to check whether you learn these things or not. Okay, and that we will consider then as a in a TAE also. Okay, so this already 10:30. Thank you very much for listening me so patiently.
Sir, can you please share the Unit 1 notes?
Yeah, yeah. I will share this on Classroom, all notes. Okay. So I'm ending the session now. Thank you very much, guys.